beneath the breathtaking beauty of Yellowstone National Park lies a force both ancient and quietly stirring. Tourists may marvel at the sweeping valleys, steam drifting from geysers, and bison grazing peacefully on sunlit plains, but these serene features conceal a powerful geological mystery. Yellowstone is not just another park carved by time and weather. It is the surface expression of something far more complex, a colossal supervolcano, a vast subterranean system with the capacity to reshape not just a region, but entire continents. Let's unfold 8 critical elements that shape our current understanding of Yellowstone. Each reveals a different facet of its evolving nature, clues, signals, and movements that might indicate what lies ahead. First, we turn our eyes downward to seismic activity, the silent symphony playing beneath the soil. In March alone, Yellowstone recorded more than 70 earthquakes, most modest in scale, yet telling information. The majority were concentrated near the northern rim of the massive volcanic crater known as the caldera. 2 periods, in particular, stood out: swarms of tremors from March 3rd to 4th, and again from the 19th through the 22nd. No single event broke past a magnitude of 2.2, but that's not where the concern lies. In Yellowstone, it's not always the strength of a quake that raises attention, but its behavior. When multiple quakes cluster together in short windows of time, it hints at something moving beneath the surface, perhaps superheated fluids, or even molten rock slowly rising through ancient fractures. These swarms, though not uncommon in the park's long geological timeline, are more than statistical footnotes. They can act as preambles to increased hydrothermal activity, or as symptoms of strain building along known fault zones. Either way, their presence marks change. The location of these tremors further amplifies their significance. Some have occurred near West Yellowstone, Montana, a region resting atop fault lines with a volcanic past. It's in these familiar zones that any unusual increase in seismicity could be seen as Yellowstone's crust stretching, bending, and possibly preparing for more. Today's scientists have more tools than ever to decode what Yellowstone is saying. Seismic networks, woven through the region like invisible webs, now harness artificial intelligence to filter background noise and identify genuine geological signals. Microquakes, those too gentle for humans to feel, are logged in real time, forming an intricate digital map of activity beneath the surface. It's as though we've been given a stethoscope to listen to Earth's heartbeat, and recently, the rhythm has shifted. These networks now incorporate machine learning trained on decades of data, allowing scientists to tell the difference between normal tectonic stress and indicators of volcanic behavior. Patterns are analyzed, compared, and reanalyzed. In some recent cases, tremors have formed mirror-like sequences, which may signal pressure building from deep beneath the surface. Even more intriguing, the depth of these quakes varies widely. While most stay within 5 kilometers of the surface, a handful have occurred deeper, some beyond 10 kilometers, possibly indicating that material from the Earth's interior is making its way upward. One location that continues to draw focused analysis is the Hebgen Lake Fault Zone. Back in 1959, this area experienced a powerful and deadly earthquake. Now, over 6 decades later, new tremors are tracing the outlines of that ancient rupture. This has led experts to question whether these long, slumbering fault lines could once again become channels for rising energy, natural pathways through which heat, gas, or even magma could ascend. Are these movements the early notes of a longer geological overture? Could they mark the beginning of a slow and subtle transformation? The second major area of interest is deformation, how the land itself changes shape over time. To the naked eye, Yellowstone appears still. Mountains stand tall. Meadows sway in the wind. Nothing seems unusual. But when viewed from space, a different reality comes into focus. Advanced satellite radar and GPS stations have tracked a consistent and measurable shift since late 2024. The caldera floor, the giant bowl-shaped depression left by past eruptions, is gradually sinking. This phenomenon, known as ground subsidence, may suggest the movement of fluids below the surface or changes in pressure deep underground. The Earth's skin is not rigid here. It breathes, it contracts, and over months, those slight movements can become indicators of deeper processes at work. At first glance, Some may breathe a sigh of relief upon hearing that Yellowstone's ground appears to be slowly sinking. After all, when a volcano swells, it usually means magma is rising and building pressure beneath the surface. So wouldn't a bit of sinking suggest that tension is easing, that the threat is lessening? Not so fast. The reality beneath Yellowstone is more intricate than it seems. This caldera breathes in geological time, rising, falling, adjusting its movements driven by a complex interplay of heat, gas, fluid, and rock. The caldera's current rate of subsidence, just a few millimeters per month, may sound negligible. But the pattern is anything but uniform. Some areas are sinking faster than others. The Norris Geyser Basin, for example, is showing signs of more rapid descent, possibly indicating localized cooling, fluid redistribution, or changes in subsurface pressure. Such uneven shifts are never trivial. They suggest dynamic behavior beneath the crust, a system that is anything but dormant. To capture these subtle yet critical changes, scientists use a powerful remote sensing technique called INSAR, short for Interferometric Synthetic Aperture Radar. This tool overlays radar images from satellites taken over time, creating a visual map of how the Earth's surface is changing. Layer by layer, month after month, a portrait emerges not of a static slab, but of a living, moving system where tension and relaxation alternate like the tides. Yellowstone is not one solid mass of stone. It is a patchwork of fractured plates, floating atop a simmering sea of heat. And while vertical motion, rising or sinking, is the most obvious sign of change, it's not the only one. Horizontal deformation is also being recorded. Small, sideways slips in the Earth's crust may seem insignificant, but they often precede larger geological events. These lateral movements can result from stress along fault lines, suggesting that the park's crust is not only sinking, but also stretching. Some regions near the caldera rim exhibit asymmetrical behavior, where one side of a fault drops faster than the other. This imbalance may point to underground shifts, possibly from migrating magma or the accumulation of volatile fluids. To measure such fine-scale movements, borehole tilt meters have been embedded deep into the ground. These sensitive instruments detect the tiniest changes in slope motions that often escape traditional tools. What they've recorded recently is both fascinating and unsettling. Across parts of Yellowstone, these tilt meters have noted periodic shifts, slight tilting motions that seem to reverse over time. This cyclical behavior may reflect patterns of internal heating, followed by periods of cooling and degassing. In simple terms, Yellowstone may be inflating and deflating like a massive, breathing organism. These shifts, though measured in microradians, hold clues to the movement of heat, gas, and magma deep below the surface. It is during these quiet intervals, the slow sinking, that volcanologists grow most cautious. Because just as easily as the land sinks, it can inflate again. And history shows us that periods of calm can be followed by abrupt surges. In Yellowstone's case, subsidence can give way to inflation without warning. That sudden shift from gentle exhalation to swelling pressure is what keeps scientists on edge. This brings us to another critical signpost: hydrothermal activity, often referred to as nature's whistleblowers. These are the geysers, hot springs, and steam vents that release energy from deep below, serving as pressure valves for the subterranean system. Steamboat Geyser, the tallest active geyser in the world, remained quiet throughout March 2025. But silence does not mean inactivity. Beneath its surface, sensors have detected subtle shifts in heat and pressure. It's as if the system is preparing for another dramatic outburst. Yet Steamboat isn't the headline anymore. In the summer of 2024, rangers and scientists discovered something extraordinary: an entirely new thermal vent. Located just a mile north of the already unstable Norris Geyser Basin, this vent emerged seemingly overnight. It now emits a constant plume of steam, measured at a scorching 171 degrees Fahrenheit. In a park already known for geological volatility, the birth of a new vent is cause for close inspection. Why does this matter? Because hydrothermal systems are incredibly sensitive. A small change underground, perhaps a pocket of fluid moving into a new crack, can trigger not only the birth of new vents, but also shifts in water chemistry, pool coloration, or even violent hydrothermal explosions. The location of this new vent, so close to one of the park's most unstable regions, raises serious concerns. To monitor this development, scientists have deployed a mix of thermal imaging drones and satellite infrared scans. These technologies can detect changes in surface heat, track steam emissions, and even detect subsurface temperature anomalies. What they've seen so far is ambiguous. The vent could represent a minor adjustment in fluid pathways, or it could be the first step in a cascading process of subterranean change. When a new thermal feature appears, it often marks one of two possibilities: a benign realignment of underground heat pathways, or the early stages of larger activity, perhaps even precursors to an eruption. In a system as complex and interconnected as Yellowstone's, even small changes ripple outward. This brings us to the most startling development in recent months: our evolving understanding of the magma system itself. In early 2025, geophysicists unveiled the most detailed 3D model ever created of Yellowstone's subsurface. What they discovered surprised even the most experienced researchers. Rather than a single, enormous magma chamber as previously assumed, Yellowstone contains a sprawling, multi-chamber system. At least 7 distinct magma bodies have been identified, extending from just 4 kilometers beneath the surface down to depths over 45 kilometers. Some of these pockets are largely solidified. Others remain partially molten, mobile, active, and potentially capable of feeding future eruptions. What's more, these magma zones are not isolated. They are interconnected by a fragile web of fractures, conduits, and pressure points. A shift in one area could trigger a domino effect, sending ripples of instability through the entire system. This new understanding comes from a blend of cutting-edge techniques. Seismic tomography and wave velocity analysis allow scientists to detect differences in how seismic waves travel through rock. Slower speeds often mean the presence of molten material. Regions where wave attenuation is high, where seismic energy fades more quickly, point to areas of partially melted rock. In addition to seismic data, gravity surveys and magnetotelluric imaging have painted an even clearer picture. These methods measure density changes and the electrical properties of underground structures, revealing previously hidden features such as horizontal melt sills, thin layers of molten rock trapped between denser, solidified material. These sills act as reservoirs, storing heat and gas until pressure forces them to shift. The result is a portrait of Yellowstone that is both more complex and more precarious than previously imagined: a living geological network where pressure builds silently, only to be released in unpredictable ways. Beneath Yellowstone's forests and steam-filled basins lie structures more complex than we once imagined: horizontal layers of magma, known as sills, quietly storing potential energy. These molten reservoirs, embedded between layers of older rock, can remain stable for decades or even centuries. But if disturbed by tectonic pressure, fluid injection, or thermal shifts, they could trigger changes in the entire volcanic system. A vertical surge of magma, or even lateral shifts in pressure, might be the first link in a chain reaction. What's especially compelling about the latest geological models is how closely they match the historical record. When Yellowstone has erupted in the past, it hasn't been from a single, isolated vent, it's been from multiple outlets, activating almost in unison. This suggests that beneath the surface, Yellowstone's magma system doesn't behave like a simple container. It operates more like a network, a branching, layered system of connected chambers and conduits. Stress in one zone may ripple through the others, like a hidden language of molten rock and pressure. Trying to predict when such a system might erupt is less like reading a thermometer and more like watching dominoes. Everything is connected. If Yellowstone's underground network is full of switches, scientists are now asking, how close are we to the next one being flipped? While most people look to earthquakes and lava for signs of danger, Yellowstone's surface tells its own subtle story. Every geyser, every spring, every vent is a messenger, and recently, some of those messages have grown more intriguing. During the winter of 2024 into 2025, drone-based thermal imaging surveys revealed unexpected changes. Some hot springs widened slightly. Their vibrant colors, produced by heat-sensitive microbes, shifted outward, suggesting temperature changes at the edges. Why does this matter? Because the color and clarity of Yellowstone's thermal pools are not just beautiful, they're biological indicators. The microscopic organisms living in them respond almost instantly to fluctuations in temperature, acidity, and mineral content. When their colonies move or change, it often means something deeper is shifting as well. At the Grand Prismatic Spring, one of the most iconic geothermal features in the world, researchers noted that the outer rings of microbial life have migrated outward. That could mean warming water is extending beyond its previous boundary. And it's not just one spring. Other pools near this area have undergone chemical transformations, hinting at changes in acidity and possibly increased mineral input, signs that fluids from deeper within the Earth may be rising closer to the surface. More troubling are developments near the new thermal vent discovered in mid-2024, just north of the volatile Norris Geyser Basin. The surrounding soil is now noticeably warmer, and patches of dead vegetation have grown. New bubbling puddles, once dry, have appeared. These are the surface clues of increased hydrothermal pressure and fluid migration underground. But the signs go beyond what the eye can see. Scientists have now installed time-lapse thermal cameras at key locations to monitor daily heat cycles. Springs that cool more slowly overnight may be receiving a steady flow of deeper heat, another signal of evolving geothermal dynamics. In addition, small shifts in the pH of these waters are being tracked. A minor swing in acidity can reflect major chemical reactions occurring miles beneath the crust, possibly involving new fractures or fluid channels being opened by pressurized gas or magma. Data from all these springs and geysers is collected monthly and entered into machine learning systems that look for correlations. Do spikes in acidity predict microquakes? Do shifts in temperature align with deformation events? By feeding thousands of data points into these AI systems, scientists are beginning to find early indicators that might one day help forecast activity long before it reaches the surface. Meanwhile, another layer of investigation is quietly mapping where new geothermal features are forming. Are they following random patterns, or do they cluster near fault lines and former eruption sites? So far, many new thermal anomalies are aligning with zones of known weakness in Yellowstone's crust. This could indicate rising geothermal gradients, suggesting heat is moving up, and that's not something to ignore. But perhaps the most telling signs of all come not from water or heat, but from gas. Yellowstone, like every living volcano, breathes. And its breath is made of gases: carbon dioxide, sulfur dioxide, radon, and more. When these gases change in concentration, scientists take notice. In early 2025, a network of newly installed mobile sensors began picking up a small, but statistically significant rise in carbon dioxide and radon across several regions, particularly near Norris and Mammoth hot springs. Carbon dioxide increases can mean magma is releasing gas at shallower depths, or that new cracks in the crust are allowing it to escape more easily. Radon, a radioactive gas, tends to surge when rock layers are under stress and start to fracture. On their own, small fluctuations might not seem meaningful. But when they form a trend, and especially when they occur alongside ground deformation and seismic activity, concerns deepen. Artificial intelligence systems now monitor gas emissions in real time. These systems look for patterns, repetitions, correlations, anomalies that repeat or grow. One sensor spike might be noise, but a wave of them, across multiple zones and verified by other instruments, that's a signal. A conversation between the Earth and those who know how to listen. Scientists are also taking to the skies to understand Yellowstone's breath. Aircraft equipped with infrared spectrometers now fly over the park, scanning for sulfur dioxide columns. These gas plumes are invisible to the naked eye, but carry crucial information. Combined with readings from ground stations, these aerial scans provide a layered profile from soil to sky of Yellowstone's gas emissions. And the monitoring doesn't stop there. Soil gas sensors are now embedded across key locations to track how carbon dioxide seeps through the ground. Changes in the rate or volume of this diffusion can indicate rising pressure below. When all three signals, gas, heat, and seismic movement, start aligning in the same place, that location becomes a focal point of interest. In short, Yellowstone is not silent. It is speaking in heat, in steam, in tremors, and in the breath of invisible gases. And for the scientists who are paying attention, these are not just random fluctuations. They are part of a growing body of evidence, a pattern slowly emerging from the noise. To decode these differences, researchers have begun relying on new mobile laboratories, advanced analytical stations mounted on vehicles and drones. These mobile labs allow scientists to survey wide swaths of Yellowstone in real time, collecting and analyzing air samples across diverse regions. Recently, these labs detected a subtle yet significant signal: trace amounts of helium-3. This rare isotope is a signature of gases rising from the Earth's mantle, not just from crustal magma chambers, but from the planet's deep interior. Its presence suggests that Yellowstone may be connected to a mantle plume, a vast well of heat and pressure extending far below the Earth's surface. But perhaps even more concerning is what could happen if these gases are blocked. Scientists are now modeling a scenario known as hydrothermal sealing. Over time, minerals deposited by hot fluids can begin to clog or seal the pathways through which gas escapes. Like a cork in a bottle, this sealing traps gases beneath the surface. The result: a buildup of pressure with no release valve until the system finally bursts. In such a case, gas could be released violently, even explosively. And so, with all this data, all this monitoring, all this vigilance, what would happen if Yellowstone did erupt? What would it mean not just for a park or a state, but for the world? Let's begin not with worst-case scenarios, but with something smaller. Imagine Yellowstone doesn't unleash its full fury. Instead, a more modest magmatic event takes place, still dangerous, but far from apocalyptic. Even this would be devastating. Cities like Billings, Salt Lake City, and Denver could receive inches of ash within just a few days. Airports would shut down. Thousands of flights grounded. Solar panels would be rendered useless beneath thick layers of volcanic ash. Drinking water sources could become contaminated, and power grids would strain under the weight of cascading failures. Transportation, agriculture, and commerce across the western United States would grind to a halt. Crops would be buried. Roads would become impassable. Trains and trucks, the arteries of modern economies, would be paralyzed. And that's just the beginning. Now imagine if Yellowstone experienced a full-scale super-eruption. Not a small venting of gas and ash, but the kind of eruption that has only happened a handful of times in Earth's history. The consequences would stretch far beyond the Rocky Mountains. The skies would darken. Ash would rise high into the stratosphere, circling the globe on atmospheric currents. Within weeks, sunlight would dim. Temperatures would fall. What scientists call a volcanic winter would begin, a period of global cooling that could last years. The last time Yellowstone erupted at this scale, over 640,000 years ago, it left a scar across North America. Today, the global population is infinitely more interconnected, and the consequences would be catastrophic. Crops would fail across multiple continents. Food prices would skyrocket. Trade routes would be disrupted. Aviation and shipping lanes would become unreliable. Economies would stagger under the weight of sudden scarcity. In 2024, scientists created advanced atmospheric models to simulate what such an event would look like in our modern world. The results were sobering. An eruption sending ash into the stratosphere could unleash aerosols that block solar radiation, disrupt rainfall patterns, and destabilize monsoon cycles. In some regions, especially in Africa and Southeast Asia, this could result in severe drought and famine within months. And the damage wouldn't stop with weather. The volcanic ash would infiltrate machines and buildings alike. It would clog HVAC systems, corrode electronics, and shut down turbines. Power grids would flicker and fail. Communication networks would falter. Emergency response systems, dependent on uninterrupted power, would be overwhelmed. Hospitals would see a sharp rise in respiratory illnesses as people struggle to breathe through fine ash particles. Those with asthma, lung disease, or immune conditions would be especially vulnerable. As food supplies dwindle and clean water becomes scarce, panic could spread. Migration might increase, with families fleeing from the hardest-hit regions. In more extreme cases, social unrest and political tension could rise. Conflicts over food, water, and resources could erupt. Nations might close borders. Refugee crises might unfold. The psychological trauma of displacement, of loss, of fear could rival the impact of pandemics or wars. Natural parks, forests, and protected wildlife zones would suffer greatly. Ecosystems would be transformed, some beyond recognition. And with climate disruptions spreading across continents, even species far from Yellowstone could feel the ripple effects. In such a future, global unity and rapid coordination would become the only means of stability. But history tells us that in chaos, cooperation can be fragile. All of this from a volcano that today seems quiet. And yet, in spite of these risks, Yellowstone's current status remains stable. As of April 2025, the United States Geological Survey lists the volcano at normal alert level, with an aviation color code of green. That might sound strange, even contradictory, considering all we've discussed. But it's not. Normal does not mean inactive. It means that, while signs of internal movement are present, there is no immediate evidence pointing to an eruption. The odds of a full-blown super-eruption remain astronomically low, estimated at 1 in 730,000 per year. That's less than the chance of being struck by a meteor. But Yellowstone's story is not solely about extinction-level events. Smaller hydrothermal explosions, minor magma intrusions, or significant geochemical shifts are far more likely and can still cause tremendous disruption. So why are experts so focused on Yellowstone? Because supervolcanoes don't behave like typical stratovolcanoes. They don't erupt in neatly predictable ways. They don't always announce themselves with towering plumes or lava flows. They may go quiet for centuries, then awaken suddenly, without warning. They can fracture internally. They can erupt laterally. They can split their fury between multiple vents. Today's researchers are not simply watching for one signal. They are watching for combinations, patterns across heat, gas, seismicity, and surface change. Using AI and deep data analysis, they are trying to build something we've never had before. A forecasting system that can detect the whispers before they become roars. And the question that still hangs in the air is not just if, but when. And when that time comes, will we hear the warning in time? Even with satellites orbiting above, drones flying low, and machines learning to read patterns from the deep, we remain humble students of a power far older and wiser than ourselves. Yellowstone does not provide a syllabus. There is no calendar, no fixed schedule to its movements. We can measure its breath, trace its tremors, and study its signs, but it does not owe us an explanation. Will it erupt tomorrow? Almost certainly not. The odds are incredibly low. And yet, to dismiss its activity as irrelevant would be to ignore the very nature of the Earth itself. Because Yellowstone is not a dormant relic from the past. It is active. It is shifting. It is alive. To walk through Yellowstone is to walk across a living machine, an ancient engine made not of metal and wires, but of heat and stone, gas and water. Every bubbling geyser is a pressure valve. Every trembling quake, a cog turning deep below. Every wisp of steam is a message rising from a hidden world beneath our feet. This system has been evolving for millions of years, shaped by the slow movements of tectonic plates and the deep rumble of Earth's inner fires. And here we are, humanity, standing on the surface of that machine. We place our sensors. We draw our models. We gather our data. But ultimately, we are visitors, guests, observers of something vast, beautiful, and unknowable. So we ask the question that never fully leaves our minds. Is Yellowstone simply releasing pressure, stretching its limbs after a long sleep? Or is it slowly, quietly building towards something more significant, something we may one day witness? The truth is, we do not know. But what we do know is this. Yellowstone is a reminder that the earth beneath our feet is not fixed or finished. It is restless. It is creative. It is powerful beyond imagination. And don't forget to subscribe. This channel explores the hidden forces shaping our world from the depths of ancient volcanoes to the stars above. We bring you science, story, and wonder all in one place. Because while Yellowstone may one day erupt again, today it offers us something different. A moment to reflect. A reason to listen. A chance to understand that beneath the quiet surface of the world, the Earth is always in motion. Always alive. Never still.